Today is our first lesson on part 1 of the gas laws. There are several gas laws, and we're just going to be learning about the first 3 today. As a brief introduction, the gas laws are a series of mathematical statements that relate the property of gases to each other. Okay, we mentioned in our Intro to Gases video where we learned about the behavior of gases, it's all about the P, V's, and T's, right? The P, which means the pressure of gases, the V, which means the volume of gases, and the T, which is the temperature. Okay, so what we're going to do today is we're going to focus on Boyle's law, Charles' law, and Gay-Lussac's laws, which does look at the relationships between some of these P, V's, and T's. We're going to talk about what the laws state. We're going to describe what relationship it shows between the properties that are in the equation, and then we're going to use our calculator and maybe do some practice problems on calculating what information we can get from these 3 gas laws, which is real cool. So let's get into it today. Okay, so we know we're talking about P, V's, and T's, but here's some super important points to remember when I'm solving any gas law problem. The first one, so important, all temperature units must be in Kelvin. I do not care if they give you a degree Celsius, you must convert it to Kelvin. We know that to convert from Celsius to Kelvin, I add 273. So luckily it's not a tricky unit conversion at all, but it must be in Kelvin. All right, next one is all volume units need to be the same on both sides of my gas law equation. I don't care what units of volume you have, but I do care that they are the same, or else the math will not be mathing out for us. Number 3 is all pressure units need to be the same on both sides for the same reason as my volume. Number 4, as a reminder, when I see STP, that is actually giving me numerical information. That is giving me numerical information for a temperature at standard and a pressure at standard. Okay, at standard temperature and pressure, or STP, your temperature will be equal to 273 or 0 degrees Celsius, but per gas law rule number 1 up here is that we want to make sure it's in Kelvin, so that's why I bolded the 273. And then also at 1 atmosphere of pressure. And then point number 5, if you are an honors kid, you may be asked to convert from one unit to another. If units conversions are required for these problems, do not do some rounding until the very end, which means you'll have to be getting used to kind of keeping incremental calculations in your calculator until you can use it in the further on problems to get to where you need to go. So don't round until the very end. So the first thing that kids always ask me about, oh, why does the temperature got to be in Kelvin? I'm so annoyed by that. Well, here's the deal about Kelvin. There's something called absolute zero. Absolute zero is the coldest temperature you can get, and that value is at 0 degrees Kelvin. That sounds like a great spot to start. But there are no possible temperatures lower than 0 degrees Kelvin. At 0 degrees Kelvin, atoms stop moving, okay? And matter has to be slightly in motion in some way according to the kinetic molecular theory, right? Now, if we're looking at the scale between Kelvin and 273, there's a difference of 273, right? So here we go. I've got Fahrenheit here. We're going to ignore that Fahrenheit because we do not use Fahrenheit as scientists. We use either Celsius or Kelvin. But here with my 0 degrees Kelvin absolute zero, that is equivalent to a negative 273 degrees Celsius. Y'all, we can totally have negative temperatures here in Celsius according to this scale. But we cannot use negative numbers in gas law calculations, okay? The math will not work out the way we want it to. So as a result, all gas law calculations need to have their temperature converted to Kelvin. That way I will always have a number that has a positive value and the math will work out, which is good. So Kelvin, Kelvin, Kelvin. And here, this is kind of interesting. If I were to plot a graph of volume versus temperature, what happens at 0 degrees 0 degrees Kelvin is that the volume technically of any gas would be 0 at absolute 0. Guys, I cannot have matter if matter does not have a volume. By definition, matter is anything that has mass and takes up space. Taking up space means you have to have some sort of a volume. According to this, at absolute 0, I can't have no volume, so matter cannot exist for that reason. So these next 3 gas laws are going to show how a sample of an ideal gas is affected by changing conditions. Now, we learned about what an ideal gas is last time. An ideal gas follows the kinetic molecular theory perfectly, right? We know that it is going to display no forces of attraction or repulsion with other gas particles, and the collisions that it would have with the walls of the container are going to be completely elastic with no energy being lost. Technically, the gases that exist in the real world are not perfectly ideal. They're what is known as real gases, but the calculations for real gases are really annoying and way higher level than the scope of a first year chemistry course. So we will be assuming that all of these gases are ideal going forward as we're exploring these gas laws. Now, these three gas laws, I also said, are affected, how the gas is affected over changing conditions. One thing you will consistently see is that these equations have ones on this side and twos on this side. So the one situation represents the conditions initially of the gas, and the side that has the twos represents how those conditions have changed over time. Okay, so this gives us the ability to like increase or decrease some of these values and see how it affects maybe some of the other properties of that gas. One thing to keep in mind with these three gas laws is that these gas laws also assume that the number of gas particles in my sample does not change. Okay, so it is a contained, or not a contained volume, but it is a contained number of gas molecules. I'm not putting in more gas molecules or removing them. So here I'm looking at pressure, volume, and temperature for a consistent sample of a gas during these changing conditions. So let's get into our first gas law. Woo! Boyle's law. Boyle's law looks at how pressure of a gas and how volume of a gas are related. Let's see. Okay, so Boyle's law is P1 times V1 is equal to P2 times V2, which the ones represent the initial pressures and volumes and the twos represent the final pressures and volumes. This law states that if you increase the pressure of a gas, the volume will decrease. Or if you decrease the pressure, the volume will increase. Now this is, once again, these gas laws, I'm not moving or taking away molecules, right? But this gas law only works if your temperature remains constant, meaning the temperature is going to stay the same. So here I have a real fun picture right here. Here I have a sample of a gas. Notice he is in a closed container, so no gas molecules can come in or out as a consistent sample of my gas, right? And here its pressure is 1 atmosphere, and it's got a volume of 1 liter. But here I've increased the pressure on this side to now 2 atmospheres. I've doubled the pressure, and y'all, look what happened to the volume. It halved, okay? I love to use arrows because it helps me visualize what's happening here. This side where I have a lower pressure, I have a larger volume, right? And in this side right here, I have a higher pressure and a lower volume. I'm doing this for Boyle's law. This is going to show a very important relationship between pressure and volume. So let's get into it a little bit more on Boyle's law.
In our simulation today, we're going to observe Boyle's law. So I'm going to add some particles. I'm going to add just 100, just 150. Sure, great. And then I'm going to keep my temperature constant. That's what Boyle's law tells me. I have to keep my temperature constant. And then I can see an inverse relationship between volume and pressure. So if I go ahead and I shrink the volume from what it is now, my pressure is 17.5. If I make that space a lot smaller, my pressure goes up to 35 atmospheres. So I decrease my volume, I increase my pressure, which is what you would expect, right? Those particles are colliding more, they're hitting each other more, and they're hitting the walls more because they have less space to move. If I make it a little bit bigger, my pressure goes down because I increased my volume. And if I go out even a little bit more, we can see again more volume. My pressure went down. Let's go one more time. A larger volume, and look, my pressure is all the way down to 14 atmospheres. Again, I can shrink it. As I decrease my volume, I increase my pressure. And expand it again.
A real quick explanation of Boyle's law. We have here our classic piston in a cylinder graphic here, where we trap a gas inside. One of the criteria for Boyle's law is that we keep the temperature and the number of moles of gas constant. So in this illustration, we're going to only be changing the pressure and the volume, which have an inverse relationship. If I had to state Boyle's law, that would be the direct statement of it. Pressure is inversely proportional to volume. So if we take this diagram and we allow it to compress now, we'll take the same gas, compressing it to a smaller volume, the pressure will go up. Now if we add a plot of pressure versus volume and show you a cycling where we expand and compress the gas through a cycle, you can see from this plot and the dot that we put on it that there's all these states that are possible as you go from compression to expansion. And that's an illustration of Boyle's law, and you can use it to solve lots of different gas problems.
So Boyle's law shows an inverse relationship between the pressure of a gas and the volume of a gas, as long as the temperature remains constant over that change. Now, this is an inverse relationship, so a graph for something that has an inverse relationship will always look like a slope down. This shows that as you increase the pressure, you guys, the volume is decreasing, okay? So if one value is increasing, the other decreases. If one value decreases, the other increases. This is an inverse relationship or an inverse proportion. For me, what really helps me is I kind of like to see real world examples of these gas laws in action. All around the world, y'all, we have examples of gas laws in action and how gases are affected by changes in pressure and volume and temperature. So here we're going to get into some demonstrations of Boyle's law.
In a demonstration of Boyle's law, we'll place a balloon in a vacuum bell jar. We'll apply a vacuum which basically pumps out the air in the bell jar. The pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. The air in the peep will expand to try and equalize the pressure. When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
So that's Boyle's law. Boyle's law shows the inverse relationship between the pressure and the volume of a gas under changing conditions. So now let's see if we can do the math that's required for these Boyle's law problems. All right, so we have some sample problems for Boyle's law. We have two of them. The first one, and just by the way, you guys, in these problems, you're going to get a lot of numbers. It's super important that we remember what units are indicators of pressure, volume, and temperature so we can actually label the numbers as whether they are P, V's, and T's and pick out what gas law to use. Okay, so the question states, at a pressure of 405 kPa, the volume of a gas is 6.00 liters. Assuming the temperature remains constant, at what pressure will the new volume be 4.00 liters? You're like, oh my gosh, what is even happening here? Y'all, I immediately go circle all of those numbers. Boom, 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 boom. And then based on the unit at the end of those numbers, I'm going to label them. Well, is that a unit for a pressure or volume or a temperature? kPa is a unit for a pressure. Woo! Liters is a unit for a volume. Woo! Liters is a unit for a volume. Okay? So now when I read the problem, it looks like I'm starting at a pressure of this. So this is my initial pressure or my first pressure, P1, and a volume of this. So that's my initial volume or V1. So it's assuming the temperature remains constant. Now, here's a trick. Y'all get freaked out by this statement. Guys, that just means ignore temperature. The temperature not in this problem, you should be labeled nothing as T's, okay? Assuming temperature means constant, meaning temperature is not involved here. At what pressure will the new volume be at? Here's my new volume, so this is V2. What they are asking me to solve for is my P2. They want to know what the new pressure will be at when that volume is changed to 4. Okay, so I'm like, oh cool, I got P1 and V1 and P2 and V2. Bing, 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 I've got Boyle's law. I know exactly what I need to be doing here. That's the equation I'm going to be using. And so first thing you need to do is write down the equation. P1 times V1 is equal to P2 times V2. Amazing. So now I've written my equation down and I can just substitute all of those values into the equation, making sure that you include your units. One thing to keep in mind on this substitution step, now is a good time for you to check if your units are the same if you have two of a volume, right? Both of them are in liters, which is super fine. They are the same. If one was in liters and the other one was in something else, I would have to convert them to something that was similar. It doesn't matter which, but they have to be the same going in. Okay, so my first pressure is 405 kPa. My first volume is 6.00 liters. I'm solving for P2, and my second volume is 4.00 liters, right? So when I get into my calculator, that means I am going to take the product of those. I'm going to multiply these two together, and then I'm going to divide by the 4, okay? So I get my calculator out. Let's see. I got 405 times 6 divided by that 4 from that second volume. And so here's my P2. It is 607.5. But let's have a conversation about sig figs. I'm multiplying and dividing here, which means my answer needs to be rounded to the least number of significant figures from any of the values that came into that problem. Well, it looks like everybody here has 3 sig figs, so I need to round my answer to 3 sig figs, which means I do not want that last 5. That last 5 is going to tell me to round that 7 up to an 8. So my value for my second pressure is 608, and the units are what? Don't guess, it's kPa. And the way I know that it has to be kPa is because if I plugged a pressure of kPa into this equation, the pressure unit that they're going to spit out at me has to be the exact same, okay? So kilopascals, 608 kilopascals. All right, problem number 2. It says a sample of oxygen gas occupies a volume of, oh my goodness, guys, I see a milliliters. This lets me know this is a V. At 7.40 times 10 to the second torr. Torr is a unit for P. And some of y'all are rolling your eyes being like, well, duh, ding dong, they're telling you volume is this and this is a pressure. Yes, that's wonderful, but I would not trust that completely, okay? Because sometimes they will not include those words in there. The units will always be right 100% of the time. And it also means that you don't really have to read that much, which, you know, that's great. I don't really like to read that much. So this is volume and this is pressure. Oh my gosh, these are my initial conditions, my first volume, my first pressure. Then it says, what volume will it occupy at 8.00 times 10 to the second torr pressure? So this is my new pressure, my P2. They're asking me to solve for the V2, the volume, okay? So Boyle's Law, I can totally see I got V's and P's. So my Boyle's Law equation is P1 times V1 is equal to P2 times V2. I'm ready to substitute in. My P1 value is 7.40 times 10 to the second torr. My V1 value is 2.50 times 10 to the second milliliters. My P2 value is 8.00 times 10 to the second torr. Checking to make sure my two pressures have the same units. They do. That is good news. And I'm solving for V2. Now let's have a sneaky conversation about this scientific notation. Okay, that 10 to the second means that this is technically the number 740. I threw this in here just to make sure that we are remembering how to type stuff into our calculator in scientific notation. If you would like to take these numbers out of scientific notation, that is an option for you, but I will be modeling this with our scientific notation calculator skills. So what I have here is I'm going to multiply these two numbers together and divide it by that second pressure, okay? Now, the E button in your calculator is going to help you out here with substituting in the times 10 to the part of the calculation. So what that means is I can type in 7.40, and then my second button on the calculator will allow me to activate that double E, which lets me know that that's the times 10 to the. So 7.40 E, and then whatever the exponent is, 2. And then that is all kind of understood as one thing to where I can immediately say times whatever. This allows me to use scientific notation without parentheses around the thing. So that's my first value. My second value, also in scientific notation, times 2.50 E2 equals that. And then I'm going to divide by my P2 over here, which is 8.00. I feel silly putting the 0.00, but I don't know. I feel like I'm trying to track with you guys here. E and then 2. So my answer is 231.25. Okay, rounding. It looks like everybody else going into this problem. Remember, for scientific notation, if you cover up the scientific notation part, the remaining values are all significant. So it looks like everybody has 3 sig figs going into this. So my answer is going to be rounded to 3 sig figs. So I can say V2 is equal to 231. And the units for volume, do not just guess. What were the units for volume for the first volume going into the problem? It's milliliters. So that means my units for this second volume will also be in milliliters. So this is amazing. So I've modeled here for Boyle's Law, me showing what equation I'm using. And by the way, you guys, picking out your equations, real easy to do if you do the labeling method that I've shown up here in the problem. So after you state the equation, you substitute everything in with units to check and see if the same units exist on both sides. And then you're rounding your answer to the significant figures that are required according to the values in the problem that were given to you. So that is Boyle's Law, showing how pressure and volume are related. And you know what we can do? We can even check, you guys. Look at this. This first problem here showed a larger volume, and it was turning into a smaller volume. So if the volume decreases, I would expect the pressure to increase. Did I get a bigger number for pressure on the other side? I did. So this is totally showing volume decreases, and therefore your pressure increases. Look at that, Boyle's Law. You're doing such a good job, working so hard. What about this one? What did this one show? It showed how pressure changed. Looked like that pressure went up. Oh, a pressure increased. I would expect that volume to have decreased. Let's see. Oh my gosh, it went from 250 milliliters to 231. You guys, that totally did it too. I've increased the pressure, and therefore I saw my volume decrease. Look at you, Boyle's Law, showing all the fun stuff, which is great. I love it when the math kind of supports the mentality behind some of these laws. Okay, or all of these laws, hopefully. Okay, so let's get to our next gas law. Our next gas law is Charles' Law. Charles' Law shows the relationship between how temperature and volume are related. Let's see what Charles' Law has to say. Charles' Law, it looks a little bit different. It has V1 over T1, so the initial conditions of my volume and my temperature is equal to V2 over T2. So here's the final conditions of my volume and temperature. Okay, mathematically, the way that this is set up, it tells me what the relationship is between volume and temperature. This states that if you increase the temperature, you're going to increase the volume. Or if you decrease the temperature, you're going to decrease the volume. Now, this is under the understanding that if your pressure remains constant, meaning the pressure is not changing at all during this time. So here I have a cute little picture. On this side, my picture shows a lower temperature. I can read that from the thermometer, right? And it looks like my molecules are taking up less space. Over here on the second picture, though, I've got a higher temperature, right? And, oh my gosh, my volume has taken up more space. Technically, what's happening here, we know that if we increase the temperature, I increase the average kinetic energy of the gas. If the gas particles are moving around much faster, when they're hotter, they're going to need more space to be taken up, right? So I have my down arrows and my up arrows. That means if one goes up, the other goes up. If one goes down, the others go down. So let's explore this a little bit more.
So I'm going to quickly set this up for Charles's Law. I'm going to add some particles. And now I'm going to keep my pressure constant. And then Charles' Law tells me that if I increase the temperature, I have to increase the volume. And that's because in order to do that, the pressure has to also remain constant. So I'm going to increase my temperature. And you'll notice that the size is getting bigger. And then if I decrease it, I make it smaller. The size, or the amount of space that those particles take up, is less in order to keep that pressure the same.
This is a quick illustration of Charles' Law. Charles' Law is the relationship between volume and temperature of a gas. We're going to keep the pressure constant, and we're going to keep the number of moles constant. As you see here, we have our classic illustration of piston and cylinder, where we entrap a certain volume of gas at a given pressure. In this particular diagram, we're going to now add heat to it with some fire or whatever you want to do to heat the temperature up. And then, as you can see, as the molecules become hotter, they have more force, they travel quicker, they lift the piston up to a much bigger volume. And so this illustrates the fact that when you increase temperature, you increase the volume. And then if you allow it to cool, take away the heat and allow the gas to cool, the gas will now fall back to a smaller volume as you go to a smaller temperature. So temperature and volume are directly proportional. You increase one, you increase the other. And if you want them to be directly proportional exactly, you got to use absolute temperature. So you use the Kelvin temperature. If you double the Kelvin temperature, you will double the volume. And this little illustration here shows you the volumes going up by twice and going down by half as the temperature does the same.
So Charles's law shows the direct relationship between the volume and the temperature of a gas, okay? If the volume increases, the temperature increases. If the volume decreases, the temperature decreases, okay? Now, here's a direct relationship graph or a direct proportionality graph, okay? That just shows as the temperature goes up, y'all, the volume is also going up. Same thing if I were to go down, the volume would go down. So that is what a graph for any direct relationship looks like in math or in science. Okay, it looks very different than an inverse relationship. Now, where have I seen Charles's law in action in the real world? Give me some examples that I would maybe use as a good demonstration of Charles's law in action. Let's see.
Hey folks, it's Dr. D here. In this demonstration, we're going to be looking at Charles's law, one of the gas laws. Charles's law relates the volume of a gas to its temperature. So the way that we're going to do this demonstration is we're going to use some liquid nitrogen. So I've got some liquid nitrogen right here in this container. This is called a dewar. It's like a really big fancy thermos. And I'm going to go ahead and I'm going to put on some special gloves to do this because liquid nitrogen is very cold. So it is minus 196 degrees on the Celsius scale or 77 degrees on the Kelvin scale. So that's 77 degrees above the absolute coldest temperature possible. So let me go ahead. I'm going to pour that liquid nitrogen here into this other dewar so that you can see what's going on. Now, one of the things that you might observe there in that dewar is it looks like it's boiling. And in fact, it is boiling because the temperature of that dewar is so much warmer, right? It was room temperature compared to the temperature of the liquid nitrogen that I'm pouring in there. Now, nitrogen, by the way, is about 80% of the atmosphere that we breathe, so it's most of the gas that is around you right now. All right, so I'm going to get this poured in there. We're going to allow it to stop boiling a little bit just so that it's easier for us to see. Okay, so now the next thing that we're going to do to demonstrate Charles's law is we're going to put some balloons into this liquid nitrogen. So I've got a balloon here. And what we're going to do is we're going to put this balloon into the liquid nitrogen and see what happens. We like to call these a portable air container, right? Portable gas container. So let's go ahead. Now the temperature of this gas right now is the temperature in this room, which is about 24 degrees Celsius at this point. And what we're going to do is we're going to see what happens. So you'll see already that the volume of that balloon is decreasing dramatically. And in fact, it looks like it completely, all the gas completely is gone. It's what it looks like. In fact, it's not gone. It is just reduced in volume. So if I take this out and we look at what happens to it when we warm it back up, here I'll hold it so we can watch. We're going to see that as that gas warms back up, that in fact it was still in the balloon, and it's going to refill the balloon, so it's going to return to its original volume, the volume that corresponded to the temperature in this room. Okay, so there we go. So Charles's law. Now, just to have a little bit of fun, I've got a few balloons. So we're going to see how many balloons we can stuff into this container of liquid nitrogen. So here we go. Now let's warm them up.
So that's an excellent demonstration of Charles's law. As the temperature of something decreases, that volume drastically decreased. Okay, you can also do this real fun experiment where you put a flask of a little bit of water on a hot plate and a balloon covering the top. If you heat up the water, they'll evaporate, or it'll turn into a gas and it'll expand in that balloon. Okay, as the gas temperature is actually heating up. So let's see if we can do some math with this Charles's law. Okay, it is just showing the relationship between the volume of a gas and a temperature of a gas. So we have two practice problems for Charles's law. We're going to do the same modeling strategy I've done before for Boyle's law. We're going to take each number and I'm going to label them whether they're a P, V, or a T. We're going to write our equation, we're going to substitute in our values, and we're going to solve for the answer rounding to the correct number of sig figs. But this is our first gas law that does have a temperature, so we've got to keep in mind that temperature must be in Kelvin for gas law problems. So just in case, so I always got to be aware of the Kelvin of it all, right? Okay, it says at 242 Kelvin. Oh, it looks like this is a Kelvin, a temperature, which is good. My first temperature is a Kelvin. A sample of oxygen has a volume of 325 milliliters. Milliliters is a unit for volume. So this is the volume that it was initially in, my V1. If the pressure is held constant and the temperature is lowered to 189 Kelvin, this is my second temperature, which is in Kelvin, what would the new volume of the gas be? So I'm solving for V2. Once again, do not be scared by statements like this. If the pressure is held constant, that just means, y'all, we ain't gonna have no P's in this equation, okay? So what I have labeled here is I have two T's and two V's. You were like, oh my gosh, it is magic. I know which equation I'm using. And yes, you do. You guys, we are using Charles's law, which says V1 over T1 is equal to V2 over T2. So I've stated my equation, and I'm going to be using this equation to solve for my V2. All right, I checked to make sure my temperatures are all in Kelvin. I'm ready to substitute stuff in. So my first volume was 325 milliliters. My first temperature was 242 Kelvin. I'm solving for V2, and then my second temperature is 189 Kelvin. Okay, so let's see what V2 is equal to. So mathematically, it gets a little bit sneaky when you have these fractioning equations and you're like trying to move stuff around. The way I like to think about it is like a baseball bat and a baseball, which means that the guys that are here on the crossways, you're gonna multiply them together, and then you're gonna divide by the ball. So that's like my baseball bat, and you multiply your baseball bat and you divide by your ball. Mathematically, it would work out the same if you rearrange your equation. If you were like, that sounds exhausting for my brain, like same. That's why I do my baseball and baseball bat strategy. So I have 325 times 189, right? So that's my baseball bat. And I'm going to divide by that 242. Great. My answer, how many sig figs? Everybody's got 3 sig figs. I need to round my answer to 3 sig figs. So I have 254. You're like, what are the units like? Who can possibly know? Well, what were the units for your volume of your first volume? It was in milliliters. So that means my units of my second volume need to be in the exact same. Okay. Let's see if this proves Charles's law. Charles's law is a direct relationship. Well, is this showing a direct relationship? Well, what we had is we had a change in temperature for this specific problem. Oh, it looks like the temperature went down. We decreased the temperature. Well, we would expect then the volume to decrease. Did it? Yes. So here we have a decrease in temp. Therefore, we have a decrease in volume. Yay. Good job, Charles's law. All right, let's do the next one for Charles's law. And then we'll get into our last gas law. It says a sample of nitrogen occupies a volume of 250 milliliters. I have a first volume. At 25 degrees Celsius, I have a first temperature, but stop right here. Celsius. We cannot use Celsius for our gas law problems. We need to immediately grab our calculator, and I like to do it right now so I don't forget. And so I need to add 273 to that 25. So 25 plus 273 equals 298 Kelvin. So my T1 is technically 298 Kelvin. So that's what I'll be plugging into when I get ready for my equation. What temperature? Oh, they're asking me to solve for a T2. will it be when it occupies 555 milliliters? Sorry, the milliliters is a little bit sneaky over here. I'll write that there. So this is my second volume, okay? Look at all the T's and V's. We got Charles's law coming up. So I state the equation, V1 over T1 is equal to V2 over T2. And we are using this equation to solve for our second temperature, right? So I'm ready to substitute stuff in. Are my volume units in the same? Are my volumes in the same units? Yes, they're both in milliliters. Is my temperature in Kelvin? Yes, it is. So I'm ready. So my volume, my first one is 250. Yes, that decimal after that 0 is important because it talks about how many sig figs are in the number. And then I got 298 as my first temperature. 298 Kelvin. I'm using this to solve for my second temperature, so I can go ahead and plop him on the bottom. And my second volume is 555 milliliters. Okay, so solving mathematically, I got my baseball bat, and I got my baseball. I multiply the bat together, divide by the baseball. And I go 298 times 555 equals divided by 250. And I get 661.56. How many sig figs? Everyone has 3 sig figs, including that one, because that decimal lets me know that that 0 is significant. So my answer rounded to 3 sig figs is 662. Well, what are the units? Well, it's got to match the units at the first temperature, which hopefully are in Kelvin because you did that conversion, right? So yes, the units are Kelvin. Let's see. Does this show Charles's law? Let's see. What we have done is we have changed the volume for this problem. We have increased the volume. Well, volume and temperature are directly related, so I've increased my volume. Hopefully my temperature also increased. Did it? It did. So we love that so much. Good job showing us that if I increase my volume, I will show an increase in temperature. That is great. Okay, our last gas law of the day. Let's figure out what our last gas law is. Our last gas law is Gay-Lussac's law. It shows how temperature and pressure of a gas are related. So let's see what Gay-Lussac's law says. Oh my gosh, mathematically, Gay-Lussac's law is P1 over T1, meaning my initial pressure and my initial pressure and my initial temperature is equal to P2 over T2, my final of pressure and temperature. Oh, this looks kind of similarly set up to my last law of Charles's law. Well, it's going to show a very similar relationship. This states that if I increase the temperature, I will also increase the pressure. Or if I decrease the temperature, I will decrease the pressure. Now, this only works as long as volume is held constant, meaning I'm not changing the size of the container. It's in a fixed volume, okay? So on my pictures here, I have a gas at an initial conditions of temperature and pressure and of a final condition of temperature and pressure. It looks like over here, I have a lower temperature. And let's see the pressure. Ooh, those gas particles are probably not pushing as hard on the surface of their container at a lower temperature than they would be over here at a higher temperature. As you can see, we know that increasing the temperature increases the average kinetic energy of the particles, which means they're going to be hitting the sides of those containers with a much greater force, which that's what pressure is, you guys. Okay, I got my arrows. Oh my gosh, if one is going down, the other one goes down. If one is going up, the other one goes up. That's the direct relationship that I'm seeing here between the pressure and the temperature of a gas under those changing conditions. Let's get into this a little bit more.
Hi, this is Mrs. Bustamante, and in this video, we're going to look at Gay-Lussac's law. And Gay-Lussac's law tells us that if we hold the volume constant, the amount of space that these gas particles are in take up stays the same. The pressure and the temperature are directly proportional. So I'm going to go ahead, I'm going to add just a couple particles here and we'll watch what happens. Again, my volume is constant and my temperature in Kelvin is also constant, and my pressure, while it changes a little bit, right, because the amount of collisions that are happening can vary, it remains about the same too. So if I increase my temperature a little bit, though, those particles have more energy, they're going to have more collisions, and we notice that my pressure is increasing. So I'll increase the temperature a little bit more. Again, my temperature is going up, and therefore so is my pressure. I'm down at 13, 14, 15. We see those collisions happening on their own too. Likewise, if I cool it down, right, if I make my temperature a lot cooler than it was, notice my temperature is starting to drop quite a bit and pretty quickly. My pressure is once again dropping. Again, my volume is staying the same, the amount of space that they take up is the same, and therefore the amount of collisions those particles can have. And we see that direct relationship. When the temperature goes up, the pressure goes up. And when the temperature goes down, the pressure also goes down, as long as that volume is held constant, as Gay-Lussac's law tells us.
Have you ever used a pressure cooker to make your lamb stew or that juicy pulled pork? If you own a pressure cooker, you would know that it saves you loads of time and money. And here's the physics to explain why. Take a sample of gas and trap it inside a container. This container of gas now has a fixed mass and a fixed volume. If I stick a Bunsen burner beneath this container to increase its temperature, this gives the gas particles more kinetic energy. With a greater kinetic energy, the particles can collide with the walls of the container more frequently and with more force. Since pressure is equal to force over area, an increase in the total force exerted on the walls will therefore increase the pressure inside of the container. We can conclude that the pressure of a gas is proportional to its temperature. Alternatively, we can say that pressure divided by temperature is always a constant for a particular volume of gas. So the initial pressure divided by its initial temperature is equal to the final pressure divided by the final temperature. This is one of the three gas laws of molecular kinetic theory relating pressure to temperature. To plot a graph of pressure against temperature, it's a simple linear graph to show a constant proportionality.
All right, so as we've explained with Gay-Lussac's law, his law states that pressure and temperature of a gas have a direct relationship, meaning when temperature is increased, pressure will also increase as long as volume and the number of moles of gas stays the same. So what we've done is we have increased the temperature of the gas inside of this can to boiling temperature. And I'm going to put it into this beaker of ice water, thereby decreasing the temperature of the gas in the can. Let's watch what happens to the pressure. As you can see, the pressure decreased as we decreased the temperature of the gas in the can. And since the temperature decreased and the pressure decrease caused the can to implode on itself in order to equalize pressure in the atmosphere.
So that implosion that was caused by that drastic change in temperature was an indicator of the pressure decreasing very, very, very quickly when the temperature went down, which is really cool. Let's now see if we can do some math with the Gay-Lussac's problems, okay, with the temperature and pressure of it all. So our first practice problem is at 245 Kelvin, a sample of oxygen gas has a pressure of 2.50 atm. Let's go ahead. I already see some numbers. So let's go ahead and circle them. So 245 Kelvin. Kelvin is a unit for temperature. Ooh, good thing it's already in Kelvin. If it was not, we would have to convert it, okay? So that's my first temperature. And it says it also has a pressure of 2.50 atmospheres. Atmospheres is a unit of pressure. So this is my first pressure. If the volume is held constant, remember, do not be freaked out if they say something stays the same or is held constant. That just means I will not be seeing any V's in this equation. And the temperature is lowered to 149 Kelvin. I have a new temperature. That's my second temperature. It is in Kelvin. That is good. It's always important to check what will be the new pressure of the gas. So I'm solving for P2. All right, looks like I've got T's and P's, and I'm going to be using Gay-Lussac's law, which states the first pressure over the first temperature is equal to the second pressure over the second temperature. I'll be using this equation to solve for P2. So I'm ready to substitute stuff in. My first pressure, we said, was 2.50 atm. My first temperature in Kelvin is 245 Kelvin. We're solving for P2. and my T2 is 149 Kelvin. Okay, so here's my baseball bat. I'll be multiplying these two values together and dividing it by the 245 Kelvin. So calculator up, ready to go. We've got 2.5 times 149 equals, divided by 245 equals. Okay, how many sig figs? Everybody in this problem has 3 sig figs, so I'm going to round my answer to 3 sig figs. So P2 is going to be equal to 1.52. What are the units for this second pressure? The units for the first pressure were atmospheres, so it will also be in atmospheres. Does this problem really demonstrate the relationship between pressure and temperature according to Gay-Lussac's law? Let's see. Well, we know it's a direct relationship. What happened here was I lowered the temperature. If I lowered the temperature, I should expect that the pressure also lowered. And yes, in fact, that is what I've seen. So that's always good. Okay, so we have lowered, where'd my pencil lead go? My pencil lead disappeared. Here we go. So if I've lowered the temperature, therefore, I will see a lowering in my pressure. Thank you, Gay-Lussac. All right, our last problem, our last gas law problem for the day. It says a sample of gases at STP when the pressure is raised to 775 torr and the volume remains constant. What will the new temperature of the gas be? The first thing I notice in this problem is that there are not as many numbers as I was expecting. But they did write something super interesting. Do y'all see this STP? STP actually can give you some numerical information depending on if I may need a temperature or a pressure or even both. Well, let's see what the problem is actually having us do here. It says they want us to say when the pressure is raised to 775 torr, torr is a unit of pressure, I'm raising it to that. So this is actually my second pressure. That's what's happened after the change. And the volume remains constant. Ignore volume remaining constant. What will the new temperature of the gas be? So we're solving for the new temperature, the T2. So now I modeled this out first before I unpacked what information I can get from this STP because I need to see what my values are for after the change. I'm dealing with a pressure and a temperature. So STP, I'm going to be taking my first temperature and my first pressure from this. Okay, standard temperature is going to be my T1. We know standard temperature is 273 Kelvin. Standard pressure, I most remember standard pressure as 1 atmosphere, but looking at this over here, I've given you your second pressure in torr. We know we want my units for a pressure to be the same on both sides of the equation. Doesn't matter what they are, but I know that 1 atmosphere is equal to 760 torr. That is an equality statement that I can make. So I can, at STP, I know that my first pressure is 1 atmosphere or 760 if the units are in torr. So yeah, I've got everything I need here. I've got my 2 temperatures, I've got my first pressure, and now I've got my 2 pressures, I've got my first temperature, and I'm solving for the second temperature. So my equation, P1 over T1 is equal to P2 over T2. I'm solving for T2. Substitute everybody in. Our first pressure was our STP pressure, which was 760 torr. Our first temperature was our STP temperature, which is 273 Kelvin. My second pressure is 775 torr, and I'm solving for T2. Okay, here's my baseball bat, and here's my baseball. Multiply the bat together and divide by the ball. So we got 273 times 775 equals, and then divide by 760. Okay, so that's what my calculator gives me. Everybody in here has 3 sig figs going into this. So my second temperature is 278. The units for temperature are going to be the same as the first temperature, and they're always also going to be in Kelvin, which is really good. Okay, now, so that's our answer. Does this describe or show that Gay-Lussac's law works in terms of the relationship between pressure and temperature? Well, what I've had here is I had an increase in pressure. If I've increased the pressure, we know that the temperature should also increase. And yes, that's what I've seen. It's increased its temperature as well. So that's Gay-Lussac's law, our first 3 gas laws. Let's kind of summarize what it is that we've learned here today. So with our first three gas laws, we have Boyle's law, which shows that pressure and volume are inversely proportional. If one goes up, the other goes down. We have Charles's law, which says that if temperature and volume are directly proportional, if one goes up, the other goes up. If one goes down, the other goes down. And then finally, Gay-Lussac's law shows that temperature and pressure are directly proportional as well. If one goes up, the other goes up. If one goes down, the other goes down. These are our first three gas laws. Y'all, it is all about the P, V's, and T's.